Alright, so let's wrap up BJTs now. So I'm going to show off here our first few slides that we're going to skip, but I do want to briefly discuss their content. When you actually make a BJT, you diffuse in dopants just like we did when we made a simple PN junction. So that's why we always had, for example, P plus and N doping, is because we start with an N-type silicon boule, cut it into wafers, put it in a furnace, and then diffuse in boron to make the P-type layer. And you have to put more boron than there was phosphorus down here, so that's why you get P+. And so I'll skip details on this slide, but one of the findings is that when you do a diffusion type doping that you see here, where here's my background concentration, this is a PNP BJT where the substrate is P-type and that's my collector. The base is N-type, which is right here, and the emitter is P+, which is right here. Okay, and so the current flow would be in this direction. You can see that these are diffused in, and so here's my background concentration for the wafer. I diffused in my phosphorus with high temperature, and I diffused in boron here with high temperature to make my P+ region. So I get P+, N, and P whenever the doping levels exceed the previous doping level. Well, the key point when this is, and I skipped the math, is that if you do this, because of diffusion, you end diffusion because you have a changing concentration across here, you actually get an electric field profile across the base. And this works in our favor because if I have holes that are injected by diffusion to here, we already know that they will diffuse across the base region by diffusion, high concentration here, low concentration here. But now I've got this extra electric field to kick them across there at even higher velocities. And so in the previous lecture I talked about that record-breaking transistor, and they said in the write-up for that, they said that basically they use this graded doping profile to enhance transport of carriers across the base. Okay, now let's look at something that I do want to go into detail on, the effect of base narrowing. So, let's examine how the base width might change as we increase our emitter-collector voltage. And so if I'm putting voltage on this, again I'm putting a voltage across the emitter and collector, and I notice that I'm forward biasing the emitter base, so all the voltage drop will be across the collector. Well, for this simple case here, I've assumed it's a P plus N P plus, so these are heavily doped. That means all the depletion width will be into the lightly doped region, which is the base. And so here's my base width in terms of the N-type material. It goes from 0 to LB. That's my full length of my N-type material, and all the depletion is into the N-type material. I'm going to add a term here, L, which is the width of the base collector depletion region, and my base width then is going to therefore be decreasing as L increases. Okay? So it's approximately my base width, WB, will be equal to the length of my base minus L. And so what is this L? Well, L is going to be Xn naught. Okay? So Xn naught was the amount of depletion into the N side of a PN junction, and because this is P plus N, we know all the depletion is pretty much into the N side. And so I could calculate that using this equation, and I know it'll be equal to L, as I just stated, because all the width of this depletion region is into the N side. And typically in my reverse bias, it's much greater than my contact potential, so I can just get rid of this and substitute in VBC for V naught, so I'll do that. It's also P plus N, where ND is much less than NA, so I can simplify this down to just 1 over ND. And so now I have a simple equation to give me L here as a function of voltage and doping. Now, here's the key thing, okay? Remember, as we apply voltage across the emitter collector, VEC, the voltage appears across the base collector. So as I increase VEC, I get more reverse bias voltage here, which increases L, which decreases WB. So, if WB decreases, then I know my amplification factor increases, right? We already see that here and when we calculate amplification factor. So narrower base width gives me more amplification. So, again, if we increase VEC at a fixed emitter base voltage, then the base collector voltage should increase, so WB should decrease, so my amplification factor should increase. And I'm showing that essentially right here, where I put more voltage on this thing, and you can see that the depletion region is growing and my base width is further narrowing. So how does this show up in terms of the IV characteristics? Well, if we have an increased beta as we increase VCE, so here I have my plot of collector current versus VCE, it's typical BJT transistor plot. And this is for a bunch of different IB values, so increasing IB values for each of these curves, okay? The key thing you'll notice is that as VCE increases, my amplification factor increases. So for a given base current, I'll get more collector current. And so you can see that right on this curve. Let's look at this one for example. Here's one value, here's another value, okay? So this is all for a fixed IB. This whole curve is for a fixed IB. Well, for this IB right here and this VEC, I get this much collector current, right? Now, if I increase VCE, I get base narrowing, which increases my amplification factor. So for that same level of IB, I get even more IC. And that's why as I increase VCE, I get a little bit of positive slope for my collector current characteristic shown here. If you look at a real BJT, you'll see that same increasing slope there you can see on the plot here. And what happens is if you take all the different IB values and get all these curve traces for IC versus VCE, you'll notice that they all sort of come back to a common voltage back here and cross the x-axis at a voltage called the early voltage. This is not a real voltage in the device, rather it's just the projection of the slope of these curves back into quadrant 2 here. And it basically gives you a measure of how much base narrowing you have. If I make a really good linear amplifier, I would like to have a large VA, meaning that these are very flat. That would be a really good BJT amplifier where I know the BJT is going to give me the right current for the collector, even if VCE changes some. Typically, you could also set the BJT up so VCE doesn't change, but that might not be true in all circuits. So you typically like to have a large early voltage so that your amplification factor is insensitive if VCE changes a little bit. Now, one way they achieve this is by using a graded doping. So you might ask yourself, what might that look like and how does it work? So, again, we said that when we make a BJT, if this is looking into the BJT, and we'll basically map, in this direction here, okay, so this is looking at doping, so this will be my doping for the y-axis. I would start with something like, I'll say I have a background concentration, normally that's like this, right? And then I diffuse in my n-type concentration, and then I diffuse in an even higher concentration of holes, which gives me my emitter, okay? So here's my emitter region, here's my base region, and here's my collector region. So that's a typical way you might have this. Well, the key thing here is that you have a graded doping profile here. And so this depletion width is trying to grow into the N region, right? So it's going in this direction. Well, remember, the whole point of depletion is that you have to uncover a certain amount of charge, right? Well, if the number of charges to uncover, because the doping level is increases with distance, then as I go in this direction, a given voltage will have less and less distance it needs to go to uncover the amount of charge it needs, because there's more charge density to be uncovered as the doping level increases. And so when you diffuse in a dopant like this, you can actually alleviate this base narrowing effect. I'll make one quick note. I drew this for the case of a P plus N lightly doped P scenario here, not the one shown here. But you see the same effect. Basically, this graded doping profile will reduce base narrowing because the depletion region all of a sudden starts to see all the charge it needs to grow the charge in the depletion region without having to go as much distance as it goes further into the base. Okay, we'll skip these slides as well. These are in case you want to know how the different breakdown modes for a BJT occur. My advice for you is just don't go beyond the spec sheets. Limit listed values for breakdown and maximum voltage. Okay, the last thing we're going to cover is injection level and as that relates to BJT design. So remember for PN junctions, we said at low forward bias, the depletion region can be longer than the diffusion length. And so then I get recombination in the depletion region. And so if we looked at our diode current versus voltage, here's our normal operation where I get the normal diode equation where I have this N factor being 1. So if 1 is in here, I just get QV over KT. But we said for low voltages, the depletion region is so wide that electrons and holes find each other. And for that, it was half effective at getting current flow through the device because they're recombining in the depletion region. And we showed that then you just substitute Q over 2 here, so N equals 2, so Q over 2, and your slope is half here. Well, for a BJT, this would be problematic because basically I would require then, to get the same amount of hole current, I would need more electron current coming in because electrons are recombining with holes here in the depletion region. And so my amplification factor would be decreased at low voltages because of this recombination, killing off more holes not only in the base but now also in the depletion region here as well. So for this effect, we care about the emitter base depletion region but not the base collector. Why is that? Well, we only care about this one because if I'm going to have recombination in the depletion region, I need both holes and electrons, right? And I've got some electrons going this way, so I've got both holes and electrons. This diode is reverse biased, so basically there are no electrons. It's only pretty much holes. The electron population is so small, you don't care about it. And so I mainly care about that recombination happening in the forward bias diode over here. Let's kind of pull it all together now. So again, at low voltages, some recombination occurs in the base emitter depletion region. And so if I look at all the things I care about for the BJT, emitter injection efficiency, base transport factor, current transfer ratio, and amplification factor, at low voltages and low emitter currents, I'll see that they're low. Then I get to moderate voltages, and these all reach normal values, so they go up to the normal values. But when I go to really high voltages and high emitter currents, it starts to go off again. Why is that? Well, at higher voltages, we can get so many holes and therefore electrons in the base that the exon electron concentration in the base becomes significantly higher than the background electron concentration. Basically, what I'm saying here is that if you forward bias this heavily, you're going to get a ton of holes in the base. So I'm going to have a ton of holes coming across the base. Remember, we said that every time you have a hole, one hole added, you have to add an electron, right? Because of charge neutrality. So let's say that this was doped originally, let's say 10 to the 15th in the base. Well, if I'm injecting so many holes that the concentration is 10 to the 17 holes, that requires at any given time 10 to the 17th per cc electrons. That means that this material, which was just previously lightly doped N-type at 10 to the 15, now looks like 10 to the 17th because so many electrons you have to bring in to maintain that charge neutrality with the holes. So then, instead of looking like a P plus N diode, it looks like P plus N plus. And we said that if this is P plus N plus on both sides, then I'm going to see a lot more electron current. The whole reason why I didn't have much electron current for hole current this way was because this is lightly doped. There aren't that many electrons. But again, if I pour over a ton of holes and I need charge neutrality, the electron concentration can increase to the point where I start to see lots of electrons here able to diffuse over because the concentration is so high here. And if I do that, then the whole point of having a small base current because of a high emitter injection efficiency goes away. My emitter injection efficiency decreases. If that goes down, everything goes down, and my amplification factor goes down as I go to higher current levels. Now, when we talk about higher current levels, this assumes everything is cooled. What happens if you get too hot? So things must get hot. Here's an amplifier with some BJTs and some big heat sinks. So what happens? Well, the first thing I want to do is look at where the heat dissipation is occurring here. Okay? And so if you look at a BJT and you set it up, the easiest way to tell where the power dissipation occurs is as follows. I know that the current is fairly constant from the emitter to the collector, right? Because base current's really small. So the emitter current mainly turns into collector current. So let's just say that my current is constant across here? Well, if I look at power consumption, power is current times voltage. And so what I care about is where's the current and a voltage drop. Well, the voltage drop across here is small, right? It's a forward bias diode. So not much power consumption. But look here, the voltage drop across the base collector is large. It's reverse bias. So I have current and a large voltage drop. That means a large power consumption. And you can see this beautifully here in the band diagram. I have holes, I kick them over here, they move over through the out the collector, but look what's happening here. Remember, for holes, they float up, right? So their energy, their highest energy is when they're further away. Like an electron, high energy is up here, a hole with high energy is up here. So as they get closer to the bands, they're giving up energy. Look what happens here with this hole. It moves in this direction, and as it's moving towards the collector, it is changing in energy, right? This is one energy here. This is lower energy here for a hole. So as it goes and slides across here, it's giving up energy as it slides along the hill here. So that shows you how the holes, as they go across this voltage, give up their energy before they come out the collector. And you can see the power dissipation right there. Where does this energy go? Well, it basically is transferred to the silicon atoms and basically causes them to vibrate, which is phonons, and that's what heat is. Basically, heat is just the atoms of some kind of material starting to vibrate because they're getting more and more energy. Now, this is where this gets a little bit interesting. It turns out that in a real BJT, most of a significant amount of the recombination is extrinsic, meaning it's not due to electrons and holes, it's due to defects or other things in the base which are dependent on other factors, such that the whole lifetime in the base can actually increase with temperature. Let me say it again. In many BJTs, the semiconductor quality is such that the whole lifetime in the base will actually increase with temperature, which is the opposite of classical recombination, which you increase temperature, they move around faster, they find each other faster, and they recombine faster. So and that's because of these extrinsic recombination centers, which are defects which tend to dominate the recombination. Well, if tau p goes up as temperature goes up, that means my gain increases, right? For a given amount of electrons, I'll have more holes get across, right? Without recombining. Well, if I have more gain, I get more current, right? If I get more current, then I get more power dissipation, which, wait a second, that gives me more heat and temperature, which gives me more gain and more current, which gives me more heat. And you can see that if this is not cooled, I'll get thermal runaway. The whole thing will turn to a puff of smoke. So that affects how I fabricate BJTs. With a conventional and simple BJT, you fabricate it as follows. I might start with a P-type wafer. I'll diffuse in my N-type region here, which is my base, and then I'll diffuse in the P plus emitter, which is right here. And then I'll just make contacts. My collector contact will be back here to the back side of the substrate. Here are my base contacts, and here's my emitter contact right here. The base is lightly doped, it's resistive, so I'll put a base contact on both sides. Otherwise, I'd have to have base current go all the way over here, which is a longer resistor, and would cause this BJT to be more difficult to turn it on and off, right? Now, remember, we want the base layer as thin as possible, but we also want a really large transistor area because that gives us maximum current flow, right? Current density times area is current. So it's still a big challenge getting this base current under the center of the emitter. So typically this would be very wide. This emitter would be way wide, and you're trying to get base current under that emitter. So this diagram here is misleading. So typically this region here is really wide, and you can see you have a significant resistance for this lightly doped region to get the current and electrons in the base down here in the sweet spot for operation of a current flow from the emitter to the collector. So what happens is I get current crowding here that basically most of my electrons will get to here, but they might not make it to here, and so this will be forward biased more than underneath here. I'll get more current flow here, which gives me heating, and like we said on the previous slide, that could be problematic because this could then end up causing thermal runaway. So how do we solve that? Well, if I want a large area device, what I'll do is I will basically use interdigitated electrodes, where here's my collector, here's my base region, I diffuse in my base region, then I'm going to diffuse in multiple small emitters here and make contact to all of these. And so now I've got base contacts in multiple regions, so instead of having to have base current go all the way under here, I can bring it in locally to bias this and not have to worry about the resistive base. Then I get more uniform forward biasing of the emitter base and less current crowding. What's this look like from the top? Well, here's my p-type collector here. Here's my here's my n-type base. You can see that here. And here are my p plus emitters shown up here. And here's how I make contact. Here's the base metallization contact, so this makes contact in these regions here. Here's the emitter contact. It makes contact on top of these emitter regions, and I achieve exactly what I said I would try to achieve here. So this is that device that was from Motorola. So where's my BJT in this device? Well, if you look at it, you can tell here's the interdigitation, here's my BJT. And so I've got here basically one of these is my emitter contact. I'm guessing that maybe this is the emitter contact and this is the base. And this could be my collector contact that goes down into the substrate and makes contact that way. What's this weird thing here? I think this is just a solder contact. So if you put a ball of solder here, it will this shape automatically centers it in the middle, so that when you wire bond to this thing, you'll get a nice little soldering contact just like that. And so that's why I'm guessing this is the base, because the input to the device that you would control might be a little base contact like this, but I can't tell for certain. Okay, we'll skip past this, but I will mention that a lot of classical dimmers and power supplies use something called a silicon-controlled rectifier. It's basically two BJTs wired together in a very unusual but powerful way, as you can see in these circuit diagrams, but it's beyond the scope of this class. So if you want to understand how SCRs work, you can use what you know about BJTs and look into these a little bit more deeply. Okay, that's it. Here's your review. You should be able to answer what early voltage is. You should know that in forward active mode, the heat dissipated in the BJT occurs in one region. Is it the emitter base collector, or is it everywhere uniformly dissipated? That should be easy to answer. Look at this commercial spec sheet for a PNP silicon amplifier BJT from Motorola. You should be able to answer this. Notice here that here's my DC current gain, so this is my amplification factor, and I'm increasing the collector current output, and you see that my nominal value is 100. It's lower at low voltages, right? And that's because we said that at low voltages and low currents that I get recombination in the emitter base region. But my question is, why does it perform worse at high collector values? We talked about this on a previous slides, so you should be able to answer that based on this. So you can see that the amplification factor drops off again. And lastly, to avoid current crowding, BJTs typically use what? Planar electrodes, interdigitated electrodes, or there's just no way to avoid current crowding. Okay, that's it. We are done with BJTs.